All right. This is a part of the RabbitMQ team. We decided to try something new and record some videos about the recent developments in RabbitMQ. I'm Michał, and we have Karl.
Hi, I'm Karl. I'm on the core team. Loïc?
Yeah, I'm Loïc. I work mostly with classic queues. And Iliia?
Yeah, hi, I'm Iliia. I also on RabbitMQ core team, and yeah, I love all things observability.
Awesome. All right, so we'll go through some recent releases, things we shipped, things we are working on, PRs that have been merged but not yet released, or maybe not even merged yet, work in progress. Anything that we find kind of interesting if you are in the RabbitMQ ecosystem. So the biggest news of the last few weeks is the 3.12 release. That brings a lot of improvements. There are changes to classic queues, there are changes to quorum queues, there is a much improved MQTT support and much better OAuth 2 support as well. So certainly an interesting release. One thing that we keep seeing and hearing about is that people run into an issue where they upgrade to 3.12 or they try to upgrade to 3.12 without enabling all the feature flags before that, and that won't work. There's a warning in the upgrade guide. Actually, if you go to the upgrades, there's this note here that you need to enable all feature flags before you attempt to upgrade to 3.12, not after you deploy or start 3.12. Well, actually, you should do that after the upgrade as well, because the feature flags are basically meant to, again, let's just go through the docs here. Feature flags are not meant to be a way of configuring Rabbit. Like, I don't want these features used, and therefore I don't enable them. Feature flags are, well, maybe the name is confusing, but the idea is basically just to enable rolling upgrade. So we need a way to coordinate between the nodes so that the new nodes that support a new feature don't try to use it before all nodes can support it. That's the only purpose of the feature flags. While once all the nodes support a given feature, we should just enable that. And whether we then use this feature or not is a separate question. In some cases, you have nothing to decide, like we just move from a certain version of like internal protocol to the next one. In some other cases, you are not able to use a feature without enabling the feature flag. But the point is, once you upgrade it, you enable all the feature flags, and then you're ready for the next upgrade. If you did that after 3.11 upgrade, then upgrading to 3.12 should be easy. Then you just enable all feature flags again after upgrading to 3.12. But if you didn't do that after the last upgrade and you attempt to upgrade to 3.12, unfortunately, that won't work. And we've seen a number of people asking why the upgrade failed. So yeah, certainly something to keep in mind. Going back to what's interesting in 3.12, one of the major changes is that we are no longer, there's no longer a concept of a lazy queue. That was introduced in 3.6, I believe, as a way to prevent Rabbit from keeping too many messages in memory. And basically, once you enable the lazy flag for a given queue or through a policy to a number of queues, these queues would not store messages in memory, so they would have much lower memory usage. It had some trade-offs in terms of performance, but overall that was a pretty good design. And basically in 3.12, we decided to make something similar to 3.12, basically the only option. That should prevent one of the most common support cases for us, which is Rabbit is using a lot of RAM for some reason, and I don't know why. Well, if we don't keep messages in memory, the number of situations where Rabbit can use a lot of memory is much smaller. So I'll hand over to Loïc to talk about classic queue changes in 3.12 and upcoming 3.13, because there's also some message store changes that will make it to 3.13. Loïc?
Thank you. I think I will start a little earlier because there was a lot of changes in 3.10 with the introduction of classic queues version 2, which was a work in progress, and 3.12 is more or less the completion of that work. So yes, classic queues, version 1, the main problem has always been memory. And the problem comes from mostly from the index, which keeps track of messages with a journal file as well as segment files. And it has to process all these files together. It has to make the journal and the segment files agree in order to process the messages. And when it does that, it creates a lot of garbage. And that's the extra memory and as well CPU usage that we could see. So with 3.10, we stopped, we introduced a version 2 of classic queues, which just replaced the index. And this solved part of the memory problem. We still had issues with how classic queues were built originally, which is keep messages in memory as long as there's memory space. And when there's no more memory space, push messages to disk to make room. But there's a few problems with this. The first is, of course, if you have a lot of memory, the classic queue will use all your memory and not leave any room for anything else. And then you reach the point where you break the memory threshold, and that's when RabbitMQ wakes up all the classic queues. So if classic queue is idle, it will go in hibernation to avoid, to save some memory essentially. And when we wake it up, it starts by allocating additional memory, and that can lead to a lot of issues. So when you reach the memory threshold is not typically when you want to allocate more memory, but that's what it was doing. And on top of that, writing the messages to disk also use some memory as well as some CPU. So it could lead to nodes being unresponsive for some time. So that's why lazy queues were introduced originally, but lazy queues, they were doing the opposite of classic queues, which is always write everything to disk. And they could still have messages in memory under some condition. And they would still push messages to disk when the memory threshold was reached. So there was still this hibernation and waking up issue. So to avoid this, the solution is simply to not push messages in memory. Yes, not push messages in memory to disk. But that means the queue needs to make sure it only has a certain number of messages in memory at a time. We can't let it grow indefinitely. So the end result is something that looks very similar to lazy queues, but keeps a couple thousand at most messages in memory. This way, we still benefit from the performance of having messages in memory, but we never go to a point where the queue uses way too much. And that's what is in 3.12. That applies to both classic queues v1 and v2. And in 3.13, there's additional improvements which are around the shared message store. So classic queues, when messages get are below a certain size, they are stored directly in the index. or for V2 directly in the queue in a separate store, but that's basically the same concept. They are embedded directly in the queue. When they reach a certain size, which is about 4 kilobytes by default, they are sent to a separate component, which is the message store, which is basically it's very useful for fan-out scenarios, because the message will be stored only once, not multiple times, but mostly it is optimized to write large messages to disk, unlike queues which have to do a lot of different operations and are better at storing small messages. So the message store, the optimizations that are coming in 3.13 are on two sides. One is on around reading messages from disk. So the message store, well, the queue before could read some messages directly from the message store without going through the message store, but that didn't always work, because files on the disk could be combined to save disk space. And when that happens, we can't rely on the data in those files. We can use the other files just fine, but these files are locked. And so oftentimes reading would go through the message store directly. And another thing we couldn't do before is reading many messages from the same file at once, because of complex reasons, but basically related to this combining of the files. We couldn't easily access the data on these files. And in 3.13, we no longer combine the files. We only compact a single file at once. So before we took two files, we created a source file and we put the messages still existing in this file. But in 3.13, we take one file, we take the messages at the end of the file, and we try to move them closer to the beginning. And then later on, we truncate the file to reduce the space. And doing this means that we never move the data until we truncate. We always keep, if we move a message from the end of the file to the beginning, we will for some time have the same data at the beginning and at the end. And so if a queue is reading from this file and has a location at the end of the file, it can still read this message until we truncate. And we make sure that we truncate only after all queues that have opened this file have opened the file after we moved the data, after we updated the locations. So this means that the files are no longer locked, and we can read many messages at once from the files. And so this provides a lot of performance improvements. Again, that's for messages above 4 kilobytes in size. And the other improvement in the message store is around writing. So writing, there's not much we can do better than the message store already did. We always have to go through the message store to write, but now the writes are better grouped together, and this leads to some improvements, particularly if you are using if you are not using, how do we say, if you are only sending one message and then waiting for the publisher confirm, then in this scenario, you will get better performance. And there's some other minor improvements, but nothing.
And for this one, I actually have prepared the the test results we have. So this is a difference with just these right optimizations. The yellow lines are the main, and the green is the with the right optimizations. On the high level, these are different tests running for a few minutes each. You may not notice that because when you write one message, when you publish one message and wait for confirmation, the total throughput is relatively low. So you may not notice that, but the difference is actually massive here, right? So the main can do only like 200, 250 messages a second this way. And with this optimization, you can do like 1500. So that's a massive difference, obviously.
Thank you. And yeah, that's all that's coming in 3.13. So if you have any questions or anything to discuss.
Yeah, look at that publish confirm latency as well. It's,
yeah, that's the main reason why the performance
why it goes quicker. Yeah, no, it's good. Excellent.
Not really a question, just a comment. This all still works with mirroring. We need to do quite a bit of testing to make sure that mirroring, which does a bunch of weird things internally, that all those changes don't break it. Hopefully they don't. We do test it. But there are also a few changes that I know, like you have in mind, that are basically not possible until we remove mirroring altogether.
Yes, when we remove mirroring, the classic queues no longer need to care about certain things, and that enables further optimizations. But how much this will have an impact on performance, I can't really say currently.
Yeah, I think we're all looking forward to the day when we can remove mirroring. It enables so much for us, and yeah, really held back. Thanks.
Thank you.
Cool. Well, Karl, anything to share?
Right. Yes. So I'm going to share my screen. So I was going to just talk a little bit about a couple of pull requests. They're not huge things like massive classic queue improvements or anything like that. They are quite small things. Both of them are exchange types, as it happens, which is you know, maybe a bit. Does this work? This sharing a screen like this, or should I share a specific?
It works for me. I'm not sure about the recording. Right now, it's fine for me.
Okay. Well, let's go with that. Okay, so these pull requests are not quite finished. They're not quite ready to go into release yet. So obviously, there's no promises that they will ever go into release, but there are things that we're working on, and they are working, and they are relatively likely to go into some release one day. The first one is so maybe sort of back up. RabbitMQ has a set of standard exchanges, topic and direct exchanges and so forth, as well as a behavior or an interface that you can implement to write your own exchange type. So RabbitMQ has a variety of custom exchange types as well, like the consistent hashing exchange, the random exchange, and which are moderately simple exchanges that just do routing logic, and then to more complex things like the delayed message exchange, which actually stores data, which is slightly unexpected, but that's what it does. So these two exchange types are quite simple. They just do specific routing logic to achieve two rather different use cases. So the first one is called a new local random exchange. So the RabbitMQ ships with a custom exchange type called the random exchange, and it works a little bit like a direct exchange in that you bind queues to it, But the routing key is not, the binding key is never evaluated. Instead, it simply, when you publish a message to the exchange, it simply picks a random one of all the bound queues to the exchange and tries to send it to that queue. This is suboptimal in a few ways. For example, you might have a queue on every node in a RabbitMQ cluster bound to this exchange. Given, you know, relatively uniform random selection, it means that 66% of the time you will send it to a queue that is not on the local node. That is, so you sort of have to do another network hop to deliver it to the right queue. So that obviously introduces additional latency, additional network and resource use. Also, it could well select a queue on a node that is down for maintenance, and then even if there are valid other queues on the local node or other things like that. So, in order to try to address some of those shortfalls, we've introduced this new exchange type, which works very similarly in that you bind queues to it, and it performs a random selection, but it will only perform a random selection of the queues that live on the same node as the publishing connection is connected to. So in a RabbitMQ cluster A, B, C, the 3 nodes, if you connect it to node A, it will only select a random queue from the queues that reside on node A. So this queue is very much designed to only be used with classic queues, B2s, of course. That used to be ones, not mirrored. Because quorum queues and streams are replicated queues, you don't know where their current locality is. That changes with, you know, various reasons. So this would only be used to with classic queues. And the use case that we sort of envisaged for this, there's a couple, but the main one was to provide low latency RPC type workloads. So it does mean that a publishing connection can, if you declare one of these exchanges and bind queues and declare queues on each node in the cluster, you can always publish to a local node. So you have very good availability properties. It doesn't matter what other nodes are down, you can always publish to at least one local queue. So from a publishing side, this is very convenient. It works very well. You never have to use that extra network hop. You have very good availability without having to have replication and the additional sort of latency and f-syncing costs of, say, quorum queues or the sort of the replication cost of a string queue. Where the complexity for this pattern comes in is on the consuming side, because on the consuming side, you will need to ensure, firstly, as I already mentioned, you have a queue declared and bound from every Rabbit node in order to have coverage. Secondly, you need to make sure that you have a consumer connected, and ideally a consumer should be connected on a local basis as well, so that the delivery to the consumer is also local. So if you have a cluster A, B, and C with a queue on each, you need to have a consumer connected to each, consuming from the same from the local queue. There's nothing to guarantee that you're, from a consuming point of view, that you just have to know. So there's a bit of topology knowledge that your consuming applications will have to have configured. But once you have this, you can get really great availability properties for RPC type workloads. You can even get really good scalability properties if you bind multiple classic queues to each node and have consumers that cover all the queues. You can get really good workloads. I think you did some degree of testing on that, Michał.
I did. I basically validated the concept mostly. There was 2 recent questions on the mailing list about very long queues. I would like to discuss that a bit further as well. But yeah, basically, I see no reason for that not to scale. Like, there is some inter-cluster communication always. So the larger the cluster, the more communication there is. But with this pattern, basically, there's no message related inter-cluster communication, because publisher, queue, and consumer should be on the same node. So there is no communication between the nodes on the hot path, basically. There is some coordination, as always, about like what queues exist and so on. But yeah, basically, you can scale that much, much further than the typical Rabbit cluster, which is like 3 or 5 nodes most commonly. Because again, like as it grows, and you can handle more and more traffic, but it's basically a form of sharding. Like each node performs a part of the work, but there is there's pretty much a shared nothing structure to this.
Yeah, the sharding plugin does a similar thing, but there's a few things. Again, it doesn't ensure that you necessarily end up with a local, and it can also be difficult to make sure that you have consumer coverage. I mean, RabbitMQ has got this model whereby you have a RabbitMQ cluster and you can connect anywhere and publish to anywhere, right? And we've never provided an API to do things like, at least not easily do things like, where is my queue? Where should I be connecting to? You know, we've kept it quite sort of location independent, and that's really convenient. But once you have very specific low latency or high throughput requirements, then those things start to matter. And then it becomes much more beneficial to sort of try to stay local if you can. It's a bit like having 3 non-clustered nodes, right? It's kind of almost a similar pattern to that. So that's that. It's not quite ready yet. We have some more changes to do. It might be renamed from what it is in this pull request, but it does work. As I said, Michał has tested it, and if anyone wants to test that, that's super. Any questions from Loïc or
Yeah. So regarding this node locality, what exactly like does it mean? Does it mean that consumer and publisher and RabbitMQ node should live like on the same machine? Like, in
yes.
Regarding Docker, like what locality means in Kubernetes?
By locality here in this context, we mean the publishing connection will only publish to queues that are on the same RabbitMQ node as the publishing connection. So it will never cross the network in order to deliver a message to a queue. The locality from the consumer side is something that you just have to ensure. It's not necessary, but it would be ideal. So there is nothing in this pull request that ensures that the consuming connection will be local. That's just something you have to make sure that you sort of configure your consuming applications.
If you screw up, you could end up with a situation where, let's say, the publishing is well balanced, and you have, let's say, each node handles 1/3 of the traffic, and therefore 1/3 of your messages go through one of the nodes. But then, let's say, you have 3 consuming connections. For some reason, all of them on a single node. Then you have 3 consumers consuming 1/3 of messages, and 2/3 of messages are just getting appended to the queues and never get consumed, right?
Yeah, so this still allows publishers to be completely ignorant of the RabbitMQ topology at the cost of having the consumers having to know about the RabbitMQ topology. So they need to know what nodes exist. They need to connect directly to the nodes rather than through a load balancer, for example, to ensure that they definitely do declare queues on every node. But so it's not for every use case, but it should match some use cases, especially low latency RPCs or even those that need to sort of scale out users.
Yeah.
Sir, I realized I made a mistake when I explained that, because if you have 3 consuming connections on a single node, well, you specify the queue that you want to consume from in that consumer. So you would consume all the messages, but for 2/3 of the messages, you would be consuming from a non-local node. So you lose some of the benefits, basically.
Yeah. So you introduce a network hop at the consuming side. I mean, you could imagine that we added a consumer argument to say fail if the queue I'm consuming to isn't local, right? So it would sort of allow you some sort of trial and error kind of pattern whereby you keep consuming until you hit a local, you keep trying until you hit a local node. But I think for now, let's see how this goes, and then see what else might be needed from user feedback.
So if queue and consumer queue declaration and consume call happens of the same connection, then they will be local, right? To both. Like if I start my app, open a connection to Rabbit, declare my queue, which will be bound to this exchange,
yeah,
and then start consuming, then it will satisfy all the locality.
Yeah, sure, but you have to make sure you come back to that node one if you restart the consuming app rather than another node, for example.
So they not get binned to kind of to the same.
Yeah, you need to sort of, you know,
yeah.
make the consumer know where it needs to connect.
So, but once you figure out where to connect, just a single connection, and you are kind of, there is no need to synchronize queue creation and consume, because that's the locality.
Yeah.
What is work with exclusive queues? Because then once you reconnect, you just, like with enough consumers, even if you go through a load balancer, statistically you will end up with a bunch of consumers on each node. On the publishing side, we already solved the problem by always publishing to a local one.
Yeah.
So without knowing the topology, statistically speaking, you would end up with a roughly a good balance, right?
Yeah, that would be one way to do it. Yeah, but you can also end up with, you know, when you restart, you might end up with losing these requests, right? But I mean, if the bindings disappear and there are no routes, right, returned from the exchange, then if you've got the mandatory flag, you should know pretty quickly that no routes in this node, so the publisher can then make a quick decision to, you know, retry on a different node, for example, or retry on a new connection, and see if that works. So we'll see what users sort of think of it. I know there's actually one user that's very keen on this, and it works really well for them already, even though this is not published published code, and they know the risks of taking work in progress code, but it seems to work well for them. So I'm sure it will work well for others. Should we move on to the next one? So the next one is also an exchange type, but it's for a completely different sort of aspect of the system. It's for superstreams. It's a new Murmur 3 based superstream exchange type. So this is for superstreams. So I don't know, not everyone is familiar what a superstream really is. A superstream is our solution for a partitioned stream. So a stream that has a name, and it has multiple independent partitions in order to sort of scale out the consumption load on the stream, because streams can only have don't have competing consumers like queues do. So their solution to that is to partition a single sort of entity. And the way we do that is that the superstream itself is an exchange. So it's not a first-class object in the RabbitMQ system, superstreams. Instead, it's just an exchange with a flag to say it's a superstream and a set of streams that are bound to that exchange. And in the current version of RabbitMQ, superstreams use a direct exchange for this. So I'm going to show. I've got this exchange here, a direct exchange called vegetables. And if we look at that, we can see that it's got an argument to say that it's an X superstream. So this this exchange is bound to 3 streams: vegetables 0, vegetables 1, and vegetables 2. And it's bound using a direct exchange and with a numeric routing key. So the way that superstream publishes, when they use the stream protocol, is that in the client library itself, it will find out the topology of the superstream. So it will find out how many streams there are in this superstream, and from that it will take, you know, whatever its routing material is, some sort of routing key, and it will hash that using murmur3 and to get to determine which partition it should publish a message to. Now that works very well because that's all done on the client side. It's a client side implementation. Where if you look at the routing keys here, they are the sort of the numerical values. So if you used a different protocol like an AMQP protocol to publish a message to this exchange, you could do client-side murmur3 based hashing to sort of end up with the same kind of thing, and then sort of use a routing key of the hash result. But you need to know how many partitions they are in order to do that, which isn't super easy for an AMQP client library to do. There's no means of doing that. It doesn't have knowledge of the bindings for a given exchange. That's all sort of hidden away from publishers as sort of part of the AMQP protocol. So in order to provide the same kind of abilities for non-stream protocols, we've created this superstream exchange type. So when you declare a superstream, there's now an option, there will now be an option to set the type of exchange type that you want to use for the superstream. So I'm going to do, can you see that? My shell there? Okay, so I've got this Rabbit system. I'm going to declare this superstream called fruit. I'm going to have 3 partitions like the vegetables one, but I'm setting the exchange type to X superstream. Right, so we've created a superstream with the new exchange type. So if we go to queues and streams, we see we've got fruits 0, 1, and 2. Go to exchanges, we now have this fruit exchange, and it's of the X superstream type. Okay. So if we go to that, it still has the same routing keys, but it will ignore them when you publish to it. And instead, it will take the routing key. Sorry, it really should say binding key, really, but it's got the same binding key, but it won't use that. So if we publish a message, say, if we publish a banana to the fruits exchange, we can then look here to see it went into fruit 1. Okay, so if we publish another banana to, oh, no, we can't mistype that because then it will do something else. If we publish that, it should go to the same partition, right? That's the whole idea of using a hash-based exchange type, is that keys of the same type go to the same partition. If we then publish apple instead, I tried orange, it hashed to the same value, so that wasn't a good value. Let's publish an apple, and that went to fruit 2. Right. That's the same behavior as you would get from the stream client should you publish 2 bananas and an apple to this exchange. So now this, if you use this exchange type, it is now available. You know, all your other protocols have the same murmur3 based hashing algorithm available, like a stream client has. And I do think that this is a useful change, and maybe at some point it will become the default exchange type for new superstreams. Because I do see RabbitMQ, because it's a mixed system, it's a streaming system, it's a queuing system, it does all the sort of messaging features that you kind of need for most systems. And I think systems that accept messages through a multitude of protocols into streams and then use stream consumers for efficient consumption of those, I think those kind of patterns are things that we will see a lot. So this will help get the same kind of behaviors from other protocols, and sort of level it up and make it really usable to have AMQP, MQTT ingress into streams, and then use a stream protocol consumer to consume very efficiently and do stream type work. Right. So that's the other exchange type, the superstream exchange type. Any comments or questions?
Yeah. So this is like really interesting because this client type, client-side hashing and partition reminds me Kafka, right? And with this new exchange type, partition assigning happens on server, and I wonder if it will make repartitioning or changing number of partitions easier from at least some perspectives, like client perspective, and not to know like the number of partitions on the client. Does it make it easier for server to repartition?
We don't currently support changing the number of partitions of a superstream. It's not something that's been massively requested many times. We're looking at other means of sort of scaling out consumption. Yeah, I mean, it certainly would help. From this point of view, the number of partitions or the topology of the superstream isn't a concern of a publishing AMQP or MQTT connection. They don't have to care at all. So it's all invisible to them. So that won't be a problem. The problem will be on the stream protocol side, because you need to communicate with all the connected clients to say that there's been a topology change, which is possible, but it's not something we currently support.
I'm wondering what happens if you bind this exchange to classic queues?
You just get Murmur3 based hashing of your routing key. So yeah, you can definitely use this for non superstream use cases, and maybe that means that we could, because again, this pull request is not finished, it's work in progress. Maybe it means that we'll rename it and move it into core if we think it might be useful as a generic exchange type. That certainly could be an option. Yeah.
Does it mean we would deprecate the consistent hashing exchange, or does it do something that we don't do here?
No, I don't think we will deprecate. I mean, if you look at, I think it is sharding. Sharding has got a hash-based, simple hash-based exchange as well, and but no, I don't think so. I mean, the consistent hashing exchange should, in theory, allow repartitioning better, right? It should move fewer buckets, if you like. To what degree that's important to end users, I'm not actually sure. This one wouldn't allow that. If you added another binding to this, everything might end up in a different queue, right? But with the consistent hashing exchange, that will happen to some degree as well. So yeah, you still have to be able to manage that. So, but it could be useful. Yeah. Currently, we use quite an old Murmur3 based library, like 10 years. I found some 10-year-old code that we adapted. I think in OTP 27, we'll might get Murmur3 hashing inside OTP. We'll see. And if that's the case, then maybe that would be a good time to make this a bit more efficient when it comes to the hashing part.
Why Murmur3? Like, why this particular algorithm?
That's just what Arno, our colleague Arno, chose when he when he designed and developed superstreams. That's what he chose for the hashing. It's readily available, right? It's efficient and readily available, except in where we had to rely on a library. But so it's a good hash type.
There's one topic I wanted to discuss, which is related more to the random exchange, perhaps. But we had two questions recently about how to handle very long queues, right? So we are talking, in one case, there was a specific number, which was like 80 million messages in the queue, right? We are not talking about throughput. It's just that the queue may suddenly get 80 million messages. Well, not suddenly, because you can't easily publish that many messages into a queue, but basically there are bursts that are outside of the control of the user. Like, they will happen, and then each message needs to be processed. But the interesting part is there is no ordering requirements. Like, they just all need to happen at some point. The sooner the better, but the latency is not critical. So yeah, there's a bunch of approaches where, because it's a very long queue, we immediately think about, like, well, streams are designed to handle long streams of data, queues. On the other hand, you could do some form of like sharding with the random exchange or the local exchange, and just use queues, which have the benefit that these messages are tasks. Once whatever needs to be done is done, this message is no longer needed. While with a stream, it would be still in the stream, and you need to keep track of which messages you already processed, right? So, any thoughts about like this use case?
Yeah, I mean, you could use classic queues for that if you don't need the replication for data safety, right? I mean, the likelihood of you permanently losing a disk, I don't know what they are, what the likelihood is to permanently lose your RabbitMQ disk, right? It's not even about servers anymore. In a cloud environment, you can always start another instance, right? It's more about the storage volume. I don't know what the chances are that you lose that, but relatively slim. So I mean, something like this with the classic queues could probably do it. I don't know what the upper limits, Loïc, are. What you feel about classic queues with relatively large messages?
I don't think we reached them when trying. So in the millions, at least. Yeah.
I'm not sure we tested recovery of very long classic queues right now, or well, recently. I'm not sure. Maybe you did.
That will at least take time to recover. If
there is some form of like scanning through the queue on startup.
But only if there's a crash or something similar.
Right, because that basically was the initial question, right? Like, someone was trying to use the quorum queue for that, and the quorum queue on startup needs to go through the log on disk, basically. And that means if you have a lot of messages, that log is long, and yeah, the queue startup is slow, basically.
Yeah, it can be, and that's something we already found an optimization only the other day, which probably will ship quite soon. But yeah, we'll look at a couple of design options for sort of avoiding some of that work on quorum queue recovery. But yeah, I mean, long queues will always may always require some work. Streams, obviously, they if you have a very, very large stream, it still needs to go through each segment and sort of, it's quite quick, but it still needs to do that work. There is some work that will sort of increase linearly with the length of the stream even. So quorum queues are particularly slow because they basically rebuild the state machine on startup. So, which means I have to read the entire log, and if you have lots of messages in it. But if you do so, if you shard it, right, which is, I mean, 80 million messages in a quorum queue, probably not a good idea. I probably wouldn't go over 10 million as an absolute maximum. in terms of recovery time. But if you have multiple quorum queues with fewer millions in, the recovery will work in parallel. If you have a single queue with all the messages in, it's you have to think about queues as there's an old-fashioned way of describing it, but single-threaded, right? If you have multiple queues, you can access more parallelism, and then your recovery will be a lot easier and faster. So spreading the load over multiple queues is what we've always said is a way to do stuff. So I don't know if I would use the local exchange with anything but classic queues. It may well be limited to disallow bindings from any other queue type in order to sort of really make the use case for this exchange type very, very focused. And make it less likely to be used incorrectly.
Awesome. All right.
Okay.
Iliia, any topics you would like to discuss?
Yep. So I want to talk about STOMP. So, I've been
First question.
I've been using Rabbit. I've been using Rabbit before joining the team for some years, and I mostly used it or exclusively used it as a MQP 091 broker, right? That was all about it. And I recently, by chance, I started to dig into the multi-protocol thingy. Well, the chance for this, I picked up an issue that was that sounded really simple, like add some limits to parser for the STOMP protocol, right? And well, yeah, I'm like, oh, we have STOMP. What that is? Well, and then it's turned out really, really interesting thing. So the protocol has 3 versions. The last one, 1.2, released in 2012. So it's kind of stable enough, right? By the way, do you see my screen by chance? Or not really?
You can see it.
So you see my screen, right? Yeah?
Yes.
Okay, cool. And, it's really, really simple and straightforward. Text-based resembles HTTP for a second. And when I saw it, I immediately thought about some sort of, temperature measurement device or whatever, some low power thingy that just, sends stuff without using any third-party libraries, or whatever. No binary encoding, really simple. The semantic is also simple. It has transactions that can be aborted. It can subscribe to things, send, unsubscribe. Well, yes, RabbitMQ supports it. There is a page for STOMP plugin. And what's also interesting here is that indeed it doesn't mention any limits when it describes possible configurations. And it also says that it essentially the semantic is based on MQP 091. So the protocol itself, well, is really free. When you send a message via STOMP, the destination, the semantic of destination is entirely up to server implementation. And in our case, we just follow 091, which is kind of a historical thing, right? So initially Rabbit was MQP only, and then later the other protocols were added, especially in QTT, which used MQP091 client underneath up until recently, when David and other folks moved it to native kind of APIs of Rabbit. So we now have native MQTT. We went from publishing YMQP to directly working with queues. And well, this blog post discusses all sorts of performance improvements resulting from that, including saving on many Erlang processes. So I think this is what it will be, or it is my aim for STOMP, to migrate it from MQP091 client to native API, or with focus on message containers that Karl is working. That will be a great exercise. Yeah, and well, if we go back to the original entry point for STOMP for me, that parser. Well, yeah, indeed, the parser, since the protocol is really simple, let's look at the grammar. It's indeed one of the simplest protocols I ever met. The parser was and is really beautiful, I would say. I mean, pretty much that's it. That's the whole parser. The rest is some service functions and accumulation. So we have state table and yeah, some transitions where we pick things up, like, command. We just reverse the accumulator list. Well, while working on adding the limits, yeah, the beauty of this parser is definitely lost, because we need to maintain more state, way more kind of termination points, and the nature of Erlang memory management kind of has to be considered, because well, for example, for command, we have a limited set of tokens, send, subscribe, while this parser just looks for the end of the line, keeping accumulating things up until the end of the line is seen. So this is like a bit more than needed. And well, the parser keeps state in the record, which is a tuple. And well, since it's Erlang, whenever we change a record, the new copy is created. And yeah, with all this, when we basically want to add a check for body limit or header length limit, if we use accumulators, at least either we maintain an additional counter, or we will keep doing length calculation, which is kind of too much, I guess, too. Incidentally, this limits on input data, as a limit on message size, the frame size in STOMP terms, header length limit, it's we kind of get it for free when we use STOMP web adapter that uses Cowboy for WebSockets. Well, that's because Cowboy has limits, its own limits, and the plugin exposes the limits, the settings nicely. So that's kind of, I find this interesting. And yeah, the current way of things for STOMP is unbounded input is welcome. Yeah, I wonder how serious is that for real life situation, like how many users directly use it with STOMP, I mean by TCP versus them stop STOMP users. That's kind of my discovery phase highlight.
All right, thank you. Yeah, as always, unfortunately, we have very little information about how people use Rabbit, especially when they use it successfully, because if they have issues, we at least hear about that. But if it works, we have zero information about that. So how many happy STOMP users are there? I have no idea. Every now and then I see a question that touches on STOMP, but it's almost never like a STOMP issue as such. It's just, hey, I'm using Rabbit, I'm using STOMP, and I have this problem unrelated to STOMP as such. So yeah.
It's really simple. I mean, the protocol is really simple. MQP client does all the heavy lifting. So it's no wonder that STOMP itself, doesn't do any trouble, especially since the parser actually is more forgiving than the spec itself. It allows some, more garbage interframe and the line endings like /r/n are allowed to. So that's no wonder. And yeah, if the successful STOMP usage, let us know, I guess.
So it's your sorry.
Go ahead.
So is your plan then to follow the MQTT work and work directly with queues? Yeah. Okay, that's good.
Yeah, exactly. And I think that I saw this mention on message containers PR that it says like maybe MQTT can help with dogfooding.
That's right. So David, who been involved with the MQTT stuff, is currently merging his MQTT5 work into the message container work. You're not dependent on the message container though, because you can remember right now you would, because the protocol is so simple, right? You have some headers and you have a body, right? That's pretty much it. So converting that into an AMQP message which is what you will have to do right now. It's trivial and doesn't have much overhead. So there's nothing, there's no need for you to wait for message containers
I know.
to do this work. I mean, you mentioned it, and I don't know, did you mention it, Michał, the MQTT part of 3.12 is kind of like the...
I believe I did mention that. Yeah, David didn't join today, but he was supposed to join talk about MQTT5, and I'm sure the 3.12 improvements to MQTT3 support would have been mentioned as well. But yeah, well, I guess that's something for the next episode.
Yeah. But it's a big thing for 3.12, the MQTT improvement. So yeah, but yeah, it would make sense to sort of stop bridging via AMQP North 9.1 and just go direct to queues because we can.
Karl, could you please just briefly explain what message container is? Because when I first mentioned them, I did not introduce them, so maybe somebody doesn't know what it is.
I can do. I kind of sort of are planning for the next episode maybe talk about message containers, but
the teaser.
It's basically not converting when we receive a message from a non-AMQP North 9.1 protocol, we convert it into AMQP North 9.1 kind of format, basic properties, headers, and so forth. So the idea with message containers is not to do that, and instead sort of just put the original message in its original format inside a little container type. and combine this with an implementation that allows you to sort of perform the relative conversions when delivering a message rather than when on input. So if you receive a message from MQTT in 3.11, it will, even in 3.12, it will convert it into an AMQP formatted messages and on input. And now instead, with message containers, you would be able to do that on output if you need to. So a lot of protocols may sort of have the same protocol coming in and coming out. And it's quite unnecessary in those cases to do a conversion at all, right? You kind of want the same thing coming in and coming out, especially true for AMQP 1.0 support. So message container is mostly a means for us to provide better AMQP 1.0 support in a future release. All the other protocols kind of fit into the AMQP 0.1 message type. AMQP 1.0 not so much.
Yeah, never used it. I will die thinking RabbitMQ is 0.91.
We'll see.
All right, I guess that's enough for one episode.
Excellent.
Hopefully we'll see each other soon and talk about other topics. Thanks a lot.
Thank you.
Bye.